Hello, and welcome to this training for HTTP, the Hypertext Transport Protocol. HTTP is the foundation on which the web is built, so it's important for web developers to know about it. Having a deeper understanding of HTTP will be very valuable when you're trying to troubleshoot your code. TCP/IP, which is an abbreviation for Transmission Control Protocol Internet Protocol, is the most popular networking protocol for the Internet. I'm sure you remember it from your college days. It tries to provide reliable delivery of data over an unreliable underlying network. HTTP is a TCP/IP-based protocol, and as such, it's based on the concept of sockets. A socket is one end of a two-way network connection between applications. A web server runs on a computer and has a specific socket bound to a specific port. The server waits and listens for anyone to talk to the socket. In order to talk to the server, the client, a web browser, needs to know the IP address and port of the server it wants to talk to. A port number is a 16-bit integer ranging from 1 to 65,000. Instead of looking at a web browser or web server first, let's look at a simple sockets client in .NET. We can connect to this IP address using the port 80. We send a text that says GET with the TX button, and we can receive the response with the RX button. The IP address is for example.com, which we have sent a simple garbage HTTP request. Let's go through some of the source code for the .NET application. You can see that it is setting up a perfectly ordinary TCP/IP connection using the port and IP addresses in their respective boxes and sending it the data from the third box. This is the code from the receive button labeled RX. We read the information from the socket client and put it into the bottom box. This is a simple example of a socket server where we can start listening, then send a simple empty HTTP response. In the source code, we show here what happens when you click on the listen button. When we receive the HTTP response, we put it into the text box. TCP/IP sockets are the most important pillar of the web, but another important one is DNS. Because domain names are alphabetic, they're easy to remember. But TCP/IP, our foundation for the web, is really based on IP addresses. Every time you use a domain name, a DNS service has to translate that name into an IP address. For example, the domain name www.example.com might translate to 198.105.232.4. Your computer has to start with a reference to the IP address of a DNS server. When it doesn't know a domain name, it asks that DNS server. If that DNS server doesn't know it, it asks another one up in the hierarchy. The organization that controls the root of this DNS process is called ICANN, I-C-A-N-N, the Internet Corporation for Assigned Names and Numbers. It's a non-profit corporation with an advisory committee from 111 countries. HTTP basic structure. Any type of data can be sent by HTTP as long as both the client and the server know how to handle the data content. HTTP is stateless. The client and the server only know about each other during the duration of the HTTP request. Afterwards, both of them forget. So neither the server nor the browser can retain information between different requests across web pages. The address of a World Wide Web page is a URL that you can put into the address bar of your browser to view content. A URL has the following components: the protocol, either HTTP : or HTTPS : 2 slashes, the host, which is the DNS entry that gets looked up, the port. If there's no colon, then the port is default, which is 80 for HTTP and 443 for HTTPS. The slash is optional because the URL could end here. Then the path, a question mark, and finally the query parameters. In our example here, we have HTTP as the protocol, example.com as the host. What is the port? It's 80. Then the path is skipped. Our parameters are ID equals 1, title equals home, division equals TNL. Now, what if the names or values contain special characters? What if they contain an equal sign or the ampersand? Characters like carriage return, equal sign, and ampersand all get encoded into their ASCII hex codes. In ColdFusion, you have the URL encoded format function, and in .NET, you have HTTP utility.url encode. It's not just symbols that can get encoded, it could be letters too. You'll notice that adding a parameter to a URL can make it very long. Is there a limit on how long your URL can be? In practice, you should keep it under 2,000 characters. The standard for HTTP doesn't put a hard and fast limit on the length of a URL, but you can start to run into problems with Internet Explorer and search engines at around 2,000 characters. So it's recommended that you keep the maximum around there. Parameters. We mentioned previously that HTTP is based on TCP/IP and that it's based on a stateless request-response pairing. A web page can be thought of as a function. It takes as its inputs the URL, any post parameters, and any parameters from the HTTP headers, including cookies. If there's state, it has to be reconstructed from the parameters using data from memory or database or disk. The protocol doesn't do any of this. Cookies are the key to tracking a user and giving the illusion of state. They provide the most common way to implement sessions, which we'll discuss later. HTTP structure. HTTP uses the client-server model. An HTTP client opens a connection and sends a request message to an HTTP server. The server then returns a response message, usually containing the resource that was requested. After delivering the response, the server closes the connection and the interaction ends. This makes HTTP stateless. The format of both the request and the response messages are similar. Both kinds of messages consist of an initial line, 0 or more header lines, a blank line, which is just a carriage return line feed by itself, and an optional message body, such as a file or HTML content. Here's an example of a request. You can see that there's an initial line, header lines, and the body. Here's a typical line to begin the request. The initial line is different from the request than for the response. A request line has 3 parts separated by spaces. First, the method name, in this case post, but get is the most common. The method name is always uppercase. Then the URL or path to the requested resource, and finally the version of HTTP being used. It always takes the form of http:/number.number and is uppercase. The initial line is followed by header lines, which each have a name, a colon as a delimiter, and then a value. This sample response has the same structure. The initial line here has three components. HTTP version is in the same format as the request, http:/number.number. Then the status code, 200, is meant to be computer readable. And then the reason phrase, which is meant to be human readable. The status code is a 3-digit integer. The first digit identifies the general category of the response. Most of the time, GET is what you use when looking at a web page. It's used for read operations, and it's limited in how much data you can send, as we discussed before. You won't usually use head requests. A head request is just like a GET, except it asks the server to return the response headers only and not the actual response, meaning there's no message body. You might use this if you wanted to know whether a file exists, but you didn't actually care about the contents. A POST request is used to send the data to the server to be processed in some way. Mostly it's used to write to a database, or it could be used to calculate something. In the request body is a block of data sent. There are usually extra headers to describe this message body, like content type and content length. In this case, the content type header is usually application/x-www-form-URL encoded, and the content length header gives the length of the URL encoded form data. There are other methods for REST like put and delete, but you probably won't need them. 200 OK is the normal response. The request succeeded and the resource, file, or script output is returned in the message body. 404 not found means the resource doesn't exist. 302 means that the resource has moved to another URL. The location response header tells the browser where to go. 500 server error is when you have a syntax error or another error on your page, and you get this one. Now that we've talked about the initial lines, let's go back to the header lines, which provide the information about the request or response. The header lines are in the usual text header format, which is one line per header in the form of header name, :value, ending with carriage return line feed. The header names are not case sensitive, and any number of spaces or tab may be between the colon. Some important request headers. Starting with HTTP 1.1, one server at one IP address can host several web domains. For example, host1.com and host2.com can live on the same server. Several domains living on the same server is like several people sharing a phone line. A caller needs to tell the person that answers who they're calling for. So every HTTP request must specify which host name the request is intended for, and that's what the host header does. User agent. This is how you identify which browser you're using to the web server. Potentially, the server could serve up different content to different browsers. Since organizations usually look at which browsers are looking at their site as a decision-making tool about which browsers to support, it's also a kind of vote saying, please support my browser. Some browsers allow you to fake it, so it isn't guaranteed to be true. And you can always fake it when programming HTTP requests, including when you use our web address class. Cookie. This is an HTTP cookie previously sent by the server with the set cookie response header, which we'll talk about more later. Referrer. This is the address of the previous web page from which a link to the current requested page was followed. If your site was linked to by a different site, the referrer can tell you where people are coming from. Some important response headers. Status. We already went over some of the status categories. Location. Combined with an appropriate status code, we can tell the browser to make another request to a different URL. Now, don't use server.transfer. I've never seen it used appropriately. Set cookie. This is how we tell the browser to set a stored variable and keep it for subsequent requests. We'll talk more about this one. Server. This is the equivalent of user agent, but instead of seeing the browser from the web server, you see the web server from the browser. So you could tell whether you're accessing an IIS site or an Apache site. Content type. This tells the browser how to treat the content that's returned. Is it a web page, a PDF file, a spreadsheet? Date. Caching is an important improvement in HTTP 1.1, and it can't work without time-stamped responses. So servers must timestamp every response with a date header containing the current time in the Greenwich Mean Time. Cookies. In this example excerpt from some requests and responses, we use the set cookie header in the response. This tells the browser to save the cookie and send it back in future requests to the web server. If the browser has cookies disabled, the set cookie header will be ignored. In the first request, request 1, the browser sends the request to the home page of www.example.org. The server responds with 2 set cookie headers. The first cookie is named theme. Because it doesn't have an expires attribute, it is considered a session cookie. That's a confusing term because session cookies are different from session values. But all it means is that if an expiration isn't set, the cookie will be lost as soon as the browser closes. The second cookie, session ID, contains an expires attribute, telling the browser to delete the cookie at a specific date and time. In request 2, we see that the cookie is being sent. Whenever the user goes on the website and whatever pages they visit in the interim, the cookie will be returned on every request. In addition to specifying an expiration, you can also specify other restrictions. Domain and path attributes restrict the scope of the cookie. They tell the browser what site the cookie belongs to. For security reasons, cookies can't be set for another domain. For example, example.org cannot set a cookie that has a domain of foo.com because this would allow example.org to control cookies of another domain. If a cookie's domain and path are not specified by the server, they default to the domain and path of the resource that was requested. This cookie in the example LSID has no domain attribute and a path attribute set to /accounts. The browser uses the cookie only when requesting pages contained in the /accounts folder. Another thing you might notice is HTTP only. Normally, cookies can be read and set with JavaScript. But if the HTTP only flag is present, the cookie can only be read through the HTTP response, not via JavaScript. The last thing to notice is the secure attribute. It tells the browser to include the cookie only in requests that are sent over an encrypted connection. The cookie will be missing in requests to addresses starting with HTTP, but will be included with HTTPS://requests. Here's an example of setting a cookie in ASP.NET. Fetching pages and images over the network is slow. If the browser was told to save content that doesn't change, the user's experience could be sped up. Once a page is loaded with the expires header, the browser will save the contents of the page in its cache and not request the page from the server again until the expires time is passed. This was the original way of doing caching, but because it offers very little control, the next version of HTTP had more complex ways of controlling caching. In this example, in ASP.NET, when page A is requested by the browser, the expires header tells it to save the page and use the save copy rather than making a request for a long time. Note that the caching is at the browser's discretion. If a browser is out of disk space or the user manually clears the cache, the page's contents won't be saved. The cache control header with max age is similar to the expires header in that it allows you to specify how long in seconds the browser should cache the results. The private indicator lets proxies know that the cache directive is just for the browser. In the second example, we tell the browser not to cache. The most sophisticated method of controlling caching involves something called if none match and e-tags. This method allows you to send hash codes to the browser so that it can ask the server to send the content of the page only if it has been updated. I won't be going further into this because ASP.NET does not fully support it at this point, and it's unlikely you'll want to do anything that complicated. Browser redirects. Response.redirect or CF location make major modifications to what your browser sees. When you request the page, instead of giving the page contents you were planning on, .NET or ColdFusion will totally rewrite it. You can see in this example that the whole body has been rewritten. You see that the title was specified in the code as page A, but what came out in the HTTP response was object moved. The most important thing to note is that the status code is 302 instead of the normal 200. When the browser sees a 302, it looks through the HTTP headers to find the location header. Then it makes a whole new request to the server to send whatever is specified in the location header. You won't be able to see this in the view source on the page though. Why not? As soon as the browser sees this response, the address bar will move to the next page and start requesting it. Since the next page request is already underway, there's no source code to view. Content type. HTTP can transfer many types of files. How does the browser know whether you're sending the contents of a web page or an image? In addition to looking at the file extension or just assuming you're sending HTML, the browser can also look at the content type header. Some types of files have more than one perfectly valid MIME type. Application/XML is the same as text/XML. What do you think is going to happen when we take this perfectly reasonable HTML table but tell the browser we're sending an Excel document? The browser knows that application.excel is associated with excel.exe, so it saves the page to your hard drive and runs that program, pointing it at the file it just saved. It so happens that Excel understands HTML, so after complaining about opening a disguised HTML document, Excel opens it. Content disposition is a related header that's not really standard, but it can be useful. What do you think this code does? The browser will normally open this with a Save As dialog box and suggest the file name. Fiddler. Since HTTP is a text-based protocol, we've been able to look at what requests and responses look like. What if you wanted to see under the covers of your own web browsing? Fiddler is free software that allows you to do that. It logs all the HTTP traffic between your computer and the internet. In this demo, we start up Fiddler and use it to capture traffic between my browser and this example website. The first thing we do is go to the File menu and check off Capture Traffic. Now I can browse through the site, and you can see all the traffic being logged in Fiddler. When I'm done, I can stop capturing traffic, and none of my subsequent requests will be logged. Every line that you see in Fiddler is a request-response pair. You can see the status code of the result in the list, and you can see the URL that was requested. You'll see that every time I navigate in the browser, you're getting many requests in Fiddler. There's a request for every image on the page, every JavaScript and CSS file that the page requires to render. In the request list, we can click on any of the requests that we're interested in. Then we click on the Inspector tab, and we can see the raw content of any HTTP request. Encryption. The S at the end of HTTPS stands for secure. It means that all communications between your browser and the website are encrypted. HTTPS is often used to protect highly confidential online transactions like banking and shopping order forms. All communications sent over regular HTTP connections are in plain text and can be read by anyone who intercepts communication between your browser and the website. This is especially dangerous if your credit card information or your social security number is being sent. With an HTTPS connection, all communications are securely encrypted. This means that if anyone was in a position to see your data, they wouldn't be able to decrypt it. Internet Explorer, Firefox, and Chrome all show you a padlock icon to confirm you're using HTTPS. Naturally enough, HTTPS URLs begin with https:// and they use port 443 by default, whereas HTTP URLs begin with 80 by default. Data sent over HTTPS is fully encrypted, headers included and therefore cookies. The whole URL is encrypted including the path and the parameters and GET requests. The only thing not encrypted is the host. This is because DNS is separate from HTTP, and our DNS request response when resolving the domain name is probably not. Even using encrypted communication, your browser can record the URLs you visit, and the site you're visiting can record everything about the transaction if they want. HTTPS certificates. Your browser knows how to trust HTTPS websites based on certificate authorities that your browser already trusts. There are many certificate authorities like Symantec, Komodo, and GlobalSign. In this example, the certificate correctly identifies the website. For example, when the browser visits https://example.com, the received certificate is properly for example.com and not from some other entity. Here's a normal view of Wikipedia. Notice that it's being sent over HTTPS. We can edit the host file to emulate a fake DNS entry. Now, the URL in the address bar doesn't match the host in the certificate. If we continue, in spite of this very flagrant warning, we can see that GlobalSign was the organization that provided the certificate and that it's for any subdomain of wikipedia.org. But my page is coming from mytrickhostentry.com, so there's no match and lots of complaining. Sessions. A session token is a unique identifier that's generated and sent from a server to a client to identify the current interaction session. So in other words, the session token is an ID to a record. That record could be in a database, but usually it's in memory only for a limited time that you specify. The record contains all the name-value pairs that you put into your server-side session variables. The client usually stores and sends the token as an HTTP cookie. In theory, it could be part of a URL or a post parameter, but that gets unworkable, and it's rarely done that way. Don't get this confused with the session cookie we talked about earlier that only lasts as long as the browser is open. The reason to use session tokens is that the client only has to handle the identifier. All the session data is stored in the server linked to that identifier. This makes using sessions more secure than URL variables or post variables. Now, it's tempting to use sessions as a replacement for URL and post variables, but don't do it. Users may open more than one browser that shares the same cookie. That means applications may get confused and it can cause data corruption. A second problem is that the session identifier may be stored longer in the browser than it is on the server, and the user can lose data. Compression. If you take a text file and zip it up, you get a good savings in file size. Most text-based formats compress well, often 70 to 90%. HTTP, HTML, JavaScript, and CSS are all text-based. Do you think we could get a performance improvement if we compressed our HTTP responses? People thought of this idea way back in the dial-up days. Shaving a few kilobytes off of a website was essential. With modern high-speed internet connections, it might seem like HTTP compression would no longer make sense. But sometimes, especially when using mobile devices with slow connectivity, it might. Sometimes, though, you're uploading or downloading files. Then the body of the HTTP request will be binary, and you won't get much, if any, savings at all. You also wouldn't get any savings from images, since they're a non-text format that's already compressed. One downside of using compression is that not all HTTP clients, especially programmatic ones, support it. On mobile devices, we've seen that compression can occasionally mean that a user gets a screen full of garbage instead of their content because it's not being decompressed properly. An HTTP client must explicitly request compressed content by sending the appropriate HTTP accept encoding header. If a client is not capable of HTTP compression, it will not pass that header, and the server needs to return uncompressed content. Here's an example of how you would tell ASP.NET to compress a file request for you. I've included it here for completeness and to show you that it's kind of complicated. Remember, I recommend that you not use HTTP compression because of the intermittent problems it can cause. Output buffering. This is a bonus topic because it's not technically part of HTTP, but it's related because it has to do with how your code sends the response to the browser. Like most web frameworks, ColdFusion and ASP.NET are set up by default to store content in memory until the page request is complete, and then dump it out to the client. Have a look at this snippet of code. If we were to run this page, we would see nothing for 3 seconds, and then we would see begin and end appear simultaneously. The begin and end are stored in memory, waiting for the end of the request. When the response.flush line is run, the buffer is immediately sent to the client. This means we see the begin instantly and then have to wait 3 seconds for the end. Do you think that if the page response content is big enough, that ColdFusion or .NET could run out of memory? This doesn't usually happen, but it's definitely possible. In fact, it recently happened to Brian and Dasik in ColdFusion. Using the cf_flush tag to empty the buffer solved their error. Here, we turn off the buffering and we get the same behavior as the flush example. Why is this? Well, if you don't have a buffer at all, then the response.write outputs to the browser immediately. In this example, we immediately get an error when we try to set the status code, because that value already came out in the HTTP headers. So using a flush during long page outputs will save server memory, but there's a catch. You won't be able to do a redirect after you flushed because the response status of 200 is already sent to the browser, instead of the 302 that you need to send to get the redirect. Response.clear in this example completely erases the buffer's contents, so begin doesn't even show in the output. The end.